Okay, Algebra 2 Honors, welcome back. It's great to be teaching again, although it's not quite the same as being in the classroom. Um, as I mentioned in my email, okay, this is a new experience for me. It's a new experience for you. So be patient with me. I'll be patient with you. Like I said, we're going to go slow. Um, this is, as I said, it's new, so I don't know how smoothly it will go. I think it'll be smooth. I think I've developed a good plan, but we're going to go slow. I want to make sure everyone's on the same page and we get this. We probably will not get to the same amount of material as we did, or as we would otherwise have we been in school. So we're just going to make it work, okay? And if you find yourself with a little more free time than usual, I assume you're probably not going to complain about that. I know there's some good shows out there on Netflix. I'm anxious to watch The Tiger King. If any of you have watched that, do not spoil anything for me. So what we're going to be doing today is just introducing what the graph of some of our trig functions look like. So we spent a lot of time before break, right, talking about the values of trig functions at different points, right? So what was sine of, pi over 2, or what was cosecant of 2 pi over 3? Well, you can imagine, since we have an input and an output to all of those problems, right? Our inputs were our angles, right? So sine of pi over 2 would be our angle, or our input, excuse me. And then sine of pi over 2 is 1, so 1 would be my output. You can imagine we can graph these. And then why is it important to graph these things? Well, it gives us a visual representation of the data. So you can imagine if you're trying to model something, you can think about now with all the coronavirus stuff going on, you might have seen some pictures of graphs of some exponential functions showing the number of people infected, right? So seeing a graph of something can really be a good way to visually display data. Some things can be modeled using trig functions, so it's important to know what the graphs of these things look like. So if you ever do want to model them someday using a graph, you can do so. All right, so to make things simple to start, we're going to just start with the sine graph. And we're actually not going to get to what the graphs of cosine and tangent and cotangent and all those look like. We're going to do that another day. What we're going to do today is just sine, and we're not even going to finish all of sine. We're just going to do a few different things. But what I want to start with is just to, and this will be a good review for us too, is just to fill in a little chart here with angle values and sine values. And if you find them going too fast for you, you can always stop and look back at your notes and review to see how I got some of them. But I'm just going to fill in the chart here. The x value at the top here, okay, these guys are my angles, okay? And then my y values, or my outputs, okay, are the values of the trig functions at those angles. So sine of 0 radians, if you remember, was 0. Sine of pi over 6 was 1/2. That's quadrant. We're still in quadrant 1. Sine of pi over 3 was root 3 over 2. And if you want to stop and draw your triangles just to remember how to find those values, I encourage you to do so. Sine of pi over 2, that was a quadrantal. That value is 1. 2 pi over 3, we're now in quadrant 2, which means the sine values still remain positive. And we get root 3 over 2. 5 pi over 6 is 1/2, and sine of pi is 0. Okay, now we get into, okay, quadrant 3. And remember, sine is negative in quadrant 3, so sine is 7 pi over 6. Okay, that has the same reference angle as pi over 6. And 5 pi over 6, I know it's going to be 1/2, but since we're in quadrant 3, it's going to be negative 1/2. Sine of 4 pi over 3, that has the same reference angle as what? 2 pi over 3 and pi over 3. Its reference angle is pi over 3. And since we're in quadrant 3, we're going to get negative root 3 over 2. Sine of 3 pi over 2 is a quadrantal. Get negative 1. Sine of 5 pi over 3, that's quadrant 4. Sine is still negative. 11 pi over 6. Negative 1/2, and 2 pi is 0. And remember, if we keep on going past 2 pi, we're basically back in quadrant 1, and we should start repeating our value. So what we've done is one period, right? One period of the sine function. We've done one revolution around that circle. And if we kept on going, we would get the same values again. All right, so what I want to do next is what does the graph of this look like? Right? If we were to graphically plot these points, what would they look like? And to make our lives a little bit simpler, okay, and I know this because I've done it before, I'm going to make this box pi. I'm going to basically have every box count as pi over 6. If every box counts as pi over 6, it plots it out nice and neat for us. Okay, so we have pi over 2 there. Then the next 3, if I come here, that would be pi. The next 3 over would be 3 pi over 2. And the next one over there would be 2 pi. And I'm not going to actually label every box because it gets a little bit messy, but you can imagine just count pi over 6 for each box. It allows us to space it out really nicely. So 0, let me actually do a different color here. Let's go with green for GA. At 0, I have an output of 0. So I have a point of 0. So there's 1 point. Pi over 6, that would be the next box. Pi over 6, it's 1/2. So that point right there, I'll write it above here. That point there is pi over 6, 1/2. We don't have to write that for all of them, but I just wrote it there. Pi over 3, root 3 over 2, well, root 4, right? Root 4 over 2 would equal 2 over 2, which is equal to 1. So root 3 over 2 must be less than 1. It's pretty close, though. So you can maybe plot it up there. It doesn't need to be exact. We just want a general shape of the graph. And pi over 2 is 1. Okay. So we got our first 4 points there. Let's keep going. 2 pi over 3, that would be this box here. It's should be at the same height as the point 4 pi over 2. 5 pi over 6 is 1/2, and then pi is 0. So it kind of looks like a little hill there. Let's keep on going. 7 pi over 6 is negative 1/2. 4 pi over 3 is negative root 3 over 2. It's going to be a little bit greater than negative 1, less negative, right? For the same reason that root 3 over 2 is a little bit less than 1. And then 3 pi over 2 is going to be negative 1. Again, I'm just pulling all these values from the chart above. 5 pi over 3 is negative root 3 over 2. 11 pi over 6 is negative 1/2. And 2 pi, we're back at 0. And again, you can imagine if we kept on going, these points would just repeat. So if we were actually to connect these dots, because there are points in between them, but they're just not as easy to plot. Get a nice graph that kind of takes this shape. Now, it's not perfect because I'm drawing on my iPad and it's a little bit hard to draw perfectly straight, but we kind of get this nice smooth curve. And you can imagine, I'll continue. If I were to keep on going, okay. Now, I was a little bit of an exaggeration. I shouldn't have gone down that quickly, but you can imagine this pattern is just going to keep repeating, and it kind of looks like a wave, right? And believe it or not, they actually model tides using sine and cosine curves, right? Because tides go in and out. This curve repeats. It kind of goes up and down. Kind of looks like a wave, so kind of interesting. But that is our general shape of the sine curve. A couple of unique things about it, right? It goes on forever in both directions, does not stop, okay? And it kind of looks like a wave, so kind of interesting. So let's keep on going. So some of the characteristics of a sine curve, some of them will make sense now, some of them just kind of take my word for it that they'll be more useful later on. So the curve is easily divided up into four parts. Okay, we call them the quarter periods, right? So notice on my graph above, I plotted pi over 2, pi, 3 pi over 2, and 2 pi. Really, I divided up into fourths, right? Divided up into fourths. It was really easy to divide the graph up into 4 parts. Okay, the period, right? The period of the graph is how long the graph takes to complete one cycle before it begins to repeat. We've kind of seen this before, right? The idea that once you go past 2 pi, the values start to repeat. Okay, so we call that the period in graphing, is how long the graph takes to complete one cycle. And the period of the sine function in this case is 2 pi. Okay, and I wrote here in 4, the function continues on infinitely in both directions. That's really important. It goes on forever, but most of the time we're only going to graph one period. So you only need to graph that solid green part. You don't need to keep on going or put arrows. You can just put basically endpoints at the graph, and we both will know that the graph should be continuing. Okay, so here's what the graph, here's a computer kind of generated graph of all this stuff here. And I said the sine graph can be divided up into 4 parts, 4 quarter parts. Okay. As we mentioned before, the period of the function was, the period of the function was, sorry, a little trouble there. I'm learning. 2 pi. The maximum, what's the maximum? We're talking about the maximum y value. The maximum was 1. Where did that occur? It occurred at pi over 2. Where would it occur again? If you look at the graph above, you would get a sine value of 1 at 5 pi over 2, right? And it would keep on going. When do you think the next one would be? Well, if you add 2 pi to it, you would get 9 pi over 2. And this would also work in the negative direction. Just think of all the places where sine of some angle would equal 1, okay? The minimum, what's the smallest y value? The smallest y value is -1, and that occurs at 3 pi over 2. It also would occur at 7 pi over 2, right? And we would keep on going. So there's really an infinite amount of minimum points. Increasing, decreasing. Let's hold off on that for now, just in the interest of time. Y-intercept, 0, 0. Domain, what's the domain? Well, we just kind of talked about this. Negative infinity to infinity. It does not stop. The range, -1 to 1, right? Smallest y value, -1. Largest y value, +1. The roots, right? X-intercepts occur at 0, pi, 2 pi, and I could keep on going. And conversely, it would also be -pi, -2 pi, and infinitely in that direction as well. So I'm just listing some example places here. I'm not listing, obviously, every root or every place where the max and min is 1 and -1. But also note that maxes and mins occur halfway, right? Halfway between x-intercepts, right? So if we go back to the graph above, here is a max, here is a min. I guess I'm kind of doing it the opposite way. The roots occur halfway in between the maxes and mins. Conversely, okay, let's maybe choose a different color. If I look at my roots, pi and 2 pi, what's halfway in between pi and 2 pi? It's 3 pi over 2, right? So it's divided up very nicely, hence one of the reasons we use quarter periods, because notice at the quarter period, right, first quarter period, pi over 2 is a max. If I counted another quarter of the graph over, I'm at a root. The next one, I'm at a min. The next one, I'm at a root, right? So if you divide the graph up into 4 equal parts, each one of those parts will either be a max, a min, or a root. So kind of interesting. All right, let's continue. And let's actually before we do that, let's just quickly review some of your function shifts. So if you remember back in your graphing days, I think probably this fall with Ms. Ostry, right? If you had a number, we'll call it a, right, where you multiplied some function by a, what would that do to the graph? It meant it increased, okay, your y values by a. So you'd be multiplying all your y values by a. When you added a number, c, outside the function, that meant we shifted the graph. Do you remember? You shifted the graph vertically. And then when you had one inside the function, f of x plus or minus c, when something occurred inside the function, that shifted the graph horizontally. So I just wanted to review those because they're going to show up here in a second. Okay? So a times f of x means you're increasing your y values by a factor of a. plus or minus c on the outside shifts it vertically, plus or minus c on the inside shifts it horizontally. All right, so adjusting the amplitude of the function. And we'll get to what that whole amplitude stuff means in a minute. But I want to ask you, or I want you to think about, what does the graph of 3 times sine of x look like compared to sine of x? And I would actually encourage you to maybe pause the video and just think about it if you want to in pencil. Maybe you can try even actually drawing the graph, okay? But if you just want to do it along with me here, you can do that. So let's think about this. Sine of x, we know what sine of x looks like. When I graph 3 sine of x, I'm only going to graph the quadrantal points, really the quarter period points. So if I do that, I know my sine graph's going to start at 0, 0. Okay, and actually, I'm going to do this 2 ways. If I do a regular sine graph, I know my next point would be pi over 2 comma 1. And I want to actually keep going. If I'm actually just going to draw the sine graph here. Pi comma 0. Okay, 3 pi over 2, negative 1, and then we end at 2 pi 0. And I'm actually just going to make this a dotted line because that's not actually my answer to the question, but that's the base sine function. How would 3 sine of x look different? Well, we said a minute ago, if there's a number being multiplied times the outside of the function, what it does is it increases my y values by a factor of, in this case, 3. So if you look at the point 0, 0, if the y value is 0 when I multiply 0 by 3, that means this point right here would stay the same. However, pi over 2 comma 1, what do you think that point would become? Well, if you guessed 3, you would be correct. This point would actually be way up here. Pi over 2 comma 3. I'm multiplying all my y values by 3, right? Again, and if you think about the order of operations, first you do sine of pi over 2, and sine of pi over 2 is 1, and then you would multiply 1 by 3 and get 3 as an output. Pi comma 0, multiply 0 by 3, you get the same thing. 3 pi over 2 negative 1 becomes 3 pi over 2. 3 pi over 2 negative 3. And 2 pi comma 0 become same thing, 2 pi 0. So what would this graph look like? Well, it kind of looks the same in the sense that it repeats and kind of's got this wavy look, but those hills and valleys are much steeper in this case. So the black dotted graph is sine of x. That green one is 3 sine of x. That A really begins to stretch that graph vertically. Okay, so what we say in this case is that the 3 in this case affects the amplitude. Okay, amplitude. Okay, so the amplitude of the graph, or the distance between the midline of the graph and the max and min values. We haven't talked about midline. Midline's the line that basically goes through all the root points, right? It cuts the graph in half. So in this case, my midline would be 0. So that would be an important point. Notice the sine graph starts on the midline. It started on the midline of 0. It's the line that cuts it in half. Okay, so that's what you need to know for now. The one below, negative 2 sine of x, I'm going to let you do that on your own later as part of your homework. It's a little bit slightly different. Notice it's negative 2, it's not positive 2, so I want you to think about what that might do to the graph and talk about it in your groups. You might have a disagreement, or maybe you all kind of agree on the same thing. I want to look at one more thing here, and that is adjusting the period of the function. Now, we talked about the period of the function before, okay, being how long it takes for the graph to repeat, okay? And the way you adjust the amplitude, okay, the way we adjust the amplitude is actually by multiplying some number by that x value inside. So again, as I wrote up top, if we multiply x by some constant inside the parentheses, this will adjust the period of the function. There's actually a little neat formula. We can talk about it maybe a little bit more tomorrow. But for now, I'll give you this little mini formula. 2 pi divided by b will give you the period of the function. So let's take a look at it. Let's take a look at y equals sine of 2x. What's the amplitude? What is the number multiplying the sign in front? Well, in this case, there really is no number. There's a kind of an implied 1. So my amplitude is 1. Okay. Notice in the other problem, the amplitude was 3. This one is 1. So in terms of the y values, those aren't going to change. They're going to look normally like a regular sine function does. The period, however, is going to change. So if I use my little mini formula, 2 pi, which is a normal period, and divide it by 2, 2 pi over 2 is pi, that is my new period of this function. So it's actually, this graph's going to complete one cycle quicker than a normal sine function would, which means that the quarter period, if I divide pi by 4, my quarter period is going to be pi over 4. Notice in the last graphs we were doing, we were dividing the graph up into 4 parts. The quarter periods were pi over 2. We were basically counting by pi over 2s. In this case, we're going to be counting by pi over 4s. Okay, so let's take a look. Okay, let's take a look at some of the points here. So 0, 0, okay, would be our first starting point. We're starting on the midline of 0. But where would I reach my first max point? The sine function, okay, normal sine function increases, goes up first. If I count a quarter period, my next point would be pi over 4, comma 1. And if you don't believe me, plug pi over 4 in for x. So if you plug pi over 4 in for x, I'll write it up here. We have sine of 2 times pi over 4. Well, 2 times pi over 4 is really the same thing as 2 pi over 4 or pi over 2. And we know sine of pi over 2 is 1. So you can see how that 2 really sped the function up a little bit. So we get pi over 4 comma 1. If we count another quarter period over, add a quarter period to pi over 4, we get pi over 2. Okay? And remember, on that last pattern, we always, if we counted by quarter periods, we went from we started at an intercept, then we went to a max. Oh, my pen died. So I'm going to have to do it without. Actually, no, it didn't. My fault. Pi over 4 comma 1. And then if you remember, after the max, we went back to an intercept point. So this point here, if I'm counting by quarter periods, is pi over 2 comma 0. Again, if you don't believe me, plug it in, and you'll see you'll get 0. If I count over another quarter period, my point would be 3 pi over 4, comma negative 1, and if you count over another quarter period, you get pi, comma 0. So we get the same looking graph, okay? But what's the only difference? That's not the best sine graph I've ever drawn. It should be fairly symmetrical on both sides, but I did not do a great job drawing it there. But you'll notice that to complete one cycle, it only took us pi radians to do that, where normally it takes 2 pi. So that number, that 2 there, in this function, adjusted the period. And how did I find that period? I used this little mini formula, 2 pi over the b value. Again, the b value is that number in front of the x. 2 pi divided by that b value will give you the period. To find the quarter period, how to easily divide it up? Divide it by 4. And then just start counting. Notice on a sine graph, you always start on the midline. Add a quarter period, you get to the max. Add a quarter period, you get back to the midline or an intercept. Add another quarter period, you're now at the min. Add another quarter period, you're back at an intercept. So notice the pattern. Intercept, max, intercept, min, intercept. And if we kept on going, max, intercept, min, intercept, max, intercept, min. Right? So start to notice the pattern that if you count by quarter periods, you always go from intercept, max, intercept, min, intercept, max. Okay? It's a very easy and convenient way to try to graph these. All right, the one below, y equals 2 sine of x of pi over 2. I don't know why it's doing that. Y equals sine of 2 sine of x over 2. I want you to try doing that one on your own as well. So your homework that I want you to use to do on your own, but then meet up in your groups to discuss your answers, are the 2 problems that we have not done to date. Do not go on to the section where it says shifting the function vertically. Do not need to worry about that yet. We'll get to that next class, okay? So just to repeat for homework, do the 2 problems that we have not done so far, and then at some point tonight, since we meet tomorrow, at some point tonight, you need to get together with your group, and I want you to review the answers, and then ask any questions that you have of each other. Maybe your partners can answer some of the questions that you might be having. That way, tomorrow when we meet, we can just take questions from groups themselves. At least that will be the plan. That will help streamline some of the questions and make class hopefully go a little bit smoother and a little bit quicker. Okay? So good luck with this. If you have any questions, obviously you can replay the video or rewatch certain parts, and then I will see you guys tomorrow. Make sure to check your email in the morning for the link to the Zoom virtual classroom, and I'll see you guys then.